Great. Welcome to episode 4 of the podcast. Today's topic will be a little bit more about reinforcement learning, so more of a technical topic, and to talk about the differences between predictive analytics or supervised learning and reinforcement learning. And so my thesis in this topic is that predictive analytics or supervised learning, which is much of what the AI conversation about today, is not suitable for most complex real world problems. So if you're doing sales or profit maximization for a company, for example, that would be a problem that's beyond the capability of supervised learning. And I think reinforcement learning or optimal control would be a future path, and I'll talk about that. And I think in the past, I talked about the idea of needing a causal theory. And so I'll kind of rationalize why a causal theory is required for the type of analysis or kind of profit maximization of corporations or complex systems. So let's do definitions first again. I think I talked about predictive analytics before, supervised learning. So this requires labeled training data where you have known data from the past where the outcome is known. So this could be predicting sales. For example, you would have sales by week or sales by product by week by store or some level of granularity. You'd have the data and it's been known history, so it's happened in the past, and you have the outcome, so you know what the sales number is. And then you'd have a number of variables about that you'd have for that week. Maybe you'd have, sales of other correlated products. You might have weather, time of year, price, when it was last promoted, all kinds of features that you would have. So you have a number of features that you'd have available as well. And so the idea is, can you find a mathematical relationship between the independent variable or the dependent variable, the variable that you're predicting, and the independent variables, which are the variables you're using to try to predict the outcome. So can you predict the outcome for those known records? So it's essentially curve fitting. We're looking at it. If you look at the example, the graph there on the right is modeling response by temperature, by type. It's kind of a very simple example, two-dimensional, and you can see the dots are the labels, and you're trying to fit a curve to that line. In this case, it's the line, the red or the blue line. And so in this case, you're trying to find a mathematical model, be that something complex like deep learning or a very simple regression model, a straight line, and you want to build a mathematical equation that minimizes the error on predicting the known records. So you can test this on the historical known records. So typically you can't do trade-offs. And so you can't say, let's do suboptimal for some number of records so I can do better for others. It's typically not something that you're trading off. It's a greedy approach, typically, where you're trying to minimize that error for everything. The reward, if there's a concept of reward, it's not delayed. The error is the reward. You're trying to minimize that error and you're trying to accumulate that minimum error. Typically, you're not modeling an entire system. You're typically taking samples of a system. You might be modeling a response to a direct mail campaign. So that's not looking at the whole business. So you could model, sales at the whole business level, but that would be, you're not modeling at a very granular decision-making level. Typically, it doesn't output a decision. There's a label. You're predicting a sales number. You're getting a sales number. It doesn't tell you what to do with that necessarily. There's no action that's tied to the outcome. And normally you would have to have a decision framework that you would have to wrap around a model. And so essentially it's really curve fitting of a sort, fitting data. It's really a data-driven, typically a purely mathematical exercise where you're trying to learn a pattern, a complex mathematical pattern, and fit that to the data. And so new mathematical patterns typically can only be found as quickly as you accumulate data. So, you would do a test in the market, you would collect the data, try to build the mathematical patterns, execute, collect the data. So, learning happens at the pace of time, typically, and so you're not learning faster than time because you're having to collect the labels in real time. So it's not like you can learn faster than time. So the focus on algorithms, the focus is really about algorithms and finding labeled training data, hence this kind of sea hunt for data that the whole world is on. And so that's kind of what supervised learning is. And I'll contrast that to kind of reinforcement learning and the motivation behind that. So one of the analogies for reinforcement learning was kind of a model of how animals and human beings learned, right? So as children, if you remember those shaped block toys you used to have, and you typically you see a baby playing with blocks, and you'd have try to fit a block through a hole, and you would do random trial and error. Does a star fit in the circle or the square? No. And through random trial and error, you would get the right shape and the right shaped block and the right shaped hole. And that as children, you observe the cause and effect, and you do that over and over again. And, so the first time you did it successfully, the second time you tried it, you wouldn't necessarily do it successfully again. You would iterate more and more, and you would store these experiences. So your learning would reinforce your past experience, that cause and effect. And as you do it more and more and more, you would eventually learn the pattern. So as a child develops and they've done this 100 times, then they would be able to very easily put the right block in the right shaped hole. And that's kind of a motivation for reinforcement learning. So, and as adults, we continue to do this all of our lives. And, we now know a slotted flathead screwdriver fits a flathead screw, a star-shaped screwdriver fits a star-shaped screw, a square-headed screwdriver fits a square-headed screw. This stems from a very, very earliest, perhaps, shaped learnings like this. And so that's the motivation. How do we do reinforcement learning is this. So it's driven by some trial and error and cause and effect in the real world. So typically the setup for reinforcement learning is you would have some agent, which is the learning agent that's trying to learn. You would have an environment, and the agent is taking an action, and then acting with the environment, and then the environment has a response. There's a state, the action happens, and then the environment is in a state as a result of the action. You could be accumulating reward, that the reward is success, like you were able to put the right block in the right hole. You get a reward, success, you get a 1 or a 0. Did I succeed or not? So, your action is I put the square block in the square hole, and the environment was it's that board with the holes. You got the right hole. The reward is you got the right block in the right hole. You get a reward of 1. If you got it wrong, you got a 0. And so then you learn. And so the agent is learning by exploiting what they knew in the past. So it's some combination of what you know and some combination of randomness, trial and error. And you can vary that rate so that 80% of the time you might exploit what you know, 20% of the time you might try random trial and error, or some type of trial and error, so that you can continue to learn if the environment changes. The thing about reinforcement learning is you can delay the reward from the action. And so I'll give a couple of examples of that. Typically, the agent is completely autonomous in this, that it's a setup where there doesn't have to be a human in the loop, that this can be done kind of autonomously. You can set a system up and this can simulate, and you can learn about the environment in real time by interacting with the environment in real time, like a robot learning how to walk. You can do that in real time and interact and measure that in success, or you can plan offline. And when you plan offline and simulate, you can learn faster than the pace of time, because I can simulate 100 million years of trying to play the game of AlphaGo in 1 hour if I have computing time to do that. So that's kind of the reinforcement learning setup. And if I was to speak about, let's say, a self-driving race car, be an example of reinforcement learning. You wouldn't, if you had a self-driving race car, autonomous car, you wouldn't put it on the track with an empty brain and say, learn to drive, because you'd crash a million physical cars. So how would you train the car? There's no labeled training data. You wouldn't have, a good millisecond, a bad millisecond, and collect labels around a track. Then you'd only be able to learn on tracks that you've driven on before and collected labels. And that's not a very sustainable way of doing this. So how would you do that? You would simulate racing. In the case of a race car, we know how the environment reacts. It's the laws of physics. We do have historical data about the situation. We know the air density, we know gravity, we know the friction of rubber on the road, etc. So you have the data that configures the simulation. You don't use it to create labels. And then the idea is, what are the decisions or actions I can take? In the case of a race car, it's steering position, brake pedal, gas pedal, gear. What are those actions? How do I adjust those controls to get the fastest lap around the racetrack. And so the lap around the racetrack is now a delayed reward. So what I'm doing at the beginning of the lap will affect my whole lap time, but the ultimate reward is my lap time, and that's delayed from all the actions that I take. So there's a delayed reward. And so you will make a sequence of actions, and you want to find the optimal sequence of actions. This is the policy. You want to find the policy that drives your sequence of actions that gets the fastest lap time. And so you could apply this. And so that's the setup. And the state in that case would be the position of the car, what the position of all the controls are, what gear you're in, how fast you're going, what's the position of the steering wheel, whether you're pushing brake or gas. That would be the state of the system, position, velocity, direction of the car is pointing. All of that would define the state of the environment. And then based on that, you would take an action, and with the ultimate goal of getting the fastest lap time. So that's a reinforcement learning setup. It's not a problem that you could really solve with supervised learning to my way of thinking, and maybe somebody could define a way of doing that, but I don't think that that's feasible. So that's a big difference between the types of problems you solve with reinforcement learning versus predictive modeling. Not saying that there's anything wrong with predictive modeling, it's just a different tool for a different class of problems. And so many of the problems we solve in the world are very complex, like self-driving cars, playing games, operating a business. These are things that we can apply reinforcement learning to. So if we look at the engineering domain of control theory, this is a control theory setup, which looks very much like this closed loop reinforcement learning diagram. And in the case of a control theory, in the case of a car, again, we're trying to say, what are the system inputs that we're going to take? And the system dynamics are the laws of physics to get the desired output. We want to stay on the track and have the fastest lap time. So the goal is to find the optimal set of inputs, run them through the system dynamics to get the desired system output, and we would measure the lap time. So it's very similar to a reinforcement learning setup. The mathematics is slightly different, but strongly related. So typically in engineering systems, you would say, you would say, this is the path I want to take for an autonomous car or a robot, say, this is the path I want to go. And then the computer would try to say, what actions do I take to stay on the desired path? And there'd be the optimal path that we could calculate for the fastest lap time, at a certain point in time. On lap one of the race, this is the optimal path. And as my tires degrade, that optimal path might vary. But the goal of the computer will try to stay on trajectory of the optimal path by measuring where is it currently, what's the state of the system, and it would continue to adjust that. So control theory is what engineers have done for decades. Reinforcement learning and the mathematics associated that was kind of invented, I believe, in the 1990s. Hal Sutton from the University of Alberta, wrote a book about reinforcement learning that came out in the mid 90s. I'll give a simple example of a lot of what reinforcement learning is considered kind of a Markov decision process. So this diagram here shows a Markov decision process, and it's characterized by states. So what state can the system be in? What are the actions that you can take? And the actions would transition the system from one state to another. So you have a finite set of states, you have a finite set of actions. You have some kind of transition probability between the states, like what's the probability from going from state one to state two. And then, the current state transition might be independent of any previous state transition. So that's the typical setup. So this diagram shows a state transition for a student in university. So the student is now studying for final exams, and they could go from studying, this state here, the circle that I'm highlighting, they could study and they could continue to study. That would be one transition. The reward would be -2 because the student doesn't want to study. Again, there could be another transition, study. Again, a transition -2. They could go to the pub. That's got a 0.4 transition probability. That's a reward of going to the pub. Going from the pub back to studying would be a 0.4 probability. Going from the pub back to study, so we have transition probability associated with all these. You can go from studying to browsing Facebook, if you're, I guess this or some other social media. You could completely bail and quit. You get no reward for that. So this is kind of showing, kind of transition probabilities going from one state to the next. So the idea is states, actions, and transition probability. So this is a situation where you would know all the states in advance. And so the case of a self-driving car, you could have the states would be, if you divided the steering wheel into 10 possible positions from all the way to the left to all the way to the right, you could have 10 positions of the steering wheel. You could have 10 positions of the gas pedal, 10% down, 20% down, 30% down to fully down, similar with the brake pedal. So if you imagine that times 6 gears in a car, you would have 10 steering times 10 brake times 10 gas times 6 gears. That would be 6,000 possible states. And then you would have, by observing driving, you could calculate the probability. What's the likelihood of going from steering wheel all the way to the right to all the way to the left when the gas is on the floor at 100%, which means the car would be going very fast. You're accelerating or you're driving at the maximum speed. We know from driving, you would never turn the steering wheel from all the way to the left to all the way to the right. So that transition probably would be very low, maybe even zero, that you would never see that in real driving. Whereas, going from steering wheel is most likely to be straight when you're going fast because you're going, fast and straight. And you may see the transition probability to a slight turn from steering wheel vertical to 10 degrees to the left. That might be a high transition probability because at high speed, maybe you're changing lanes. And so you can see we can define real driving would have a real set of transition probabilities depending on where the controls are and the speed of the car. So you could define in advance by observing a human being driving what all the possible states are. And then you can put that logic into a computer, and the computer could use those transition probabilities to decide how to drive. And you say, I want to stay within these lanes. That would be the objective. Or I want to get from point A to point B without crashing into anything or without going outside of my lanes. And now, given those transition probabilities that you learn from observing a human driver, you could now train a computer and do trial and error, do 100 million trials in 1 hour if you had a strong enough computer to simulate, can I get from point A to B without hitting anything and by staying in the same lane? And you can collect the reward by saying every time I'm in the same lane without leaving the lane, I can get 10 points. Every time I hit something, I lose the game, I get negative 1,000,000 points. And when I successfully get to my destination, I get plus 100 points, so something like that. And you can now simulate with those transition probabilities, and you can update those transition probabilities with the computer simulation and improve on human driving and achieve the objective. And you can set up any objective. So that would be a typical Markov decision process where you have a finite number of states and a finite number of actions. Thinking of some game trees or how many states in action. So if we think of the game of X's and O's, that game has, less than 10 actions, has 255,000 possible configurations. And so we could probably build a Markov decision process to say, if the game is in this configuration, this is the action I could take. That's a game that we could program entirely all the logic into an MDP, and the computer could learn those transition probabilities with the goal of the delayed reward to win, where winning means you get 100 points, losing means you get 0 points. And you could completely program it into an MDP. If we look at the game of chess has 10 to the 120 configurations, and there's less than maybe on the order of 100 moves that you could make at any given turn. So the number of state action pairs is massive. 10 to the 120 is huge. There's only 10 to the 80 atoms. That's a number one with 80 zeros. That's how many atoms that we believe are in the universe. That's the best estimate we have today. So 10 to the 120 chess has more possible configurations than the number of atoms in the universe. The game of Go is even more complex than chess. It has more than 10 to the 172 configurations. And so when you're playing chess and Go, if you were to try to make every configuration of the game a state and build state action rewards, this is something that'd be harder to do with a Markov decision process. You need to have some different model to model the game, or you'd have to have some reduced set of configurations, because you can't build a Markov decision model that has 10 to the 120 states. So when you get into very complex systems, this Markov decision process model, which is typically used for reinforcement learning, can't be done. So if you're looking at retail, for example, if you're doing 1 month of retail planning, let's say you have 50,000 products and you have to choose 2,000 products. 50,000 choose 2,000 is 10 to the power of 3,600. So that's even more complex than the game of Go. So the number of possible states or actions you can take is 10 to the 3,600. That's the combination of choosing 2,000 products to promote out of 50,000. And the number of configurations is even larger than that. So building a Markov decision process is not a possible solution to applying reinforcement learning or control theory. So the typical way we would then do that, engineers do, is you would go build a set of differential equations. The system dynamics in this kind of control theory setup would be a set of differential equations, not a Markov decision model that would use to define how the system works. So in the case of engineering, we have laws of physics, we have Newton's laws, we have Einstein's laws of general relativity. If we're doing space travel, we have fluid mechanics, Navier-Stokes equations for aircraft that we fly and drones, and we would use Newton's laws for cars and robots. And so there's a set of dynamics that we can model. In the case of business, we don't necessarily have business dynamics. So if I was to talk about, the dynamics that are happening in retail, these are the dynamics that we see. There's halo effect, that I've talked about in the past. Halo effect is, customer that sees ground beef. The customers don't just consume ground beef. You don't eat raw ground beef. The customer might say, "Oh, I'm going to make hamburgers. I'm going to buy hamburger buns, condiments, produce, onions, toppings. I will buy some soft drinks and French fries and things like that." So there's a whole use case with a hamburger barbecue meal that happens. So that's a halo. There's a positive halo because the customer is doing that. In the halo of ground beef, there's hamburger buns, and there's also cannibalization. Because I bought ground beef to make hamburgers, I didn't buy sausages or hot dogs. If that's what I'm making hamburgers for dinner. If I'm having a barbecue, I might buy both. But in the case of a hamburger meal, I'm not buying sausages. In the halo of ground beef, you bought hamburger buns. Those hamburgers cannibalize hot dog buns as well. The hamburger buns, because I bought hamburger buns, I didn't buy hot dog buns. So cannibalization reflects kind of a consumer choice. So cannibalization would be a negative. It also, cannibalization could apply to brand, because my family drinks Coca-Cola products. I bought Coca-Cola. We didn't buy Pepsi, so there's a cannibalization effect. So the positive halo from buying other things with the purchase creates also some negative halo, which is cannibalization reflected in choice. And once I bought, certain products have a life cycle. If I buy ketchup, the ketchup lasts for a month or two, and so I'm out of the market. So the promotional cadence will cause a forward buying effect that there's demand is taken out of the market for some period of time, or the customer stocks up because it's on sale. It's a product that they want to stock up on, doesn't go bad and spoil. I can buy 3 bottles of ketchup because it's on sale and I can store it. So there's a forward buying or pantry loading effect. So these are some retail fundamental truths. In addition to price elasticity, we know if you discount an item that you'll sell more typically if it's an elastic product. If you promote an item on the front page of your landing site, on your e-commerce site, or if you do a television ad, or you put a product in a very prominent visible place in store, promotional elasticity will cause more sales of that product. We know seasonality is an effect, that Christmas time people buy different products than they buy in the middle of the summer. So seasonality's effect, competitive, because the competitors are having stronger promotions, or they're promoting a better price point. That would have an effect. So these are all the effects. And if we assemble these into a mathematical theory, this is how we can simulate retail, these interactive effects that are happening here. In bricks and mortar retail, there's also a geographic effect, where consumers live versus where the stores are. Obviously, you're not going to drive 1,000 miles to go to the grocery store. You'll, go to the grocery store nearest to your home typically. You're not going to necessarily drive by 4 or 5 competitive grocery stores to go to the sixth one. You're more likely to choose your favorite grocery store that's reasonably close to home, where there aren't other closer choices. That's typically what happens, but there's a way to model the spatial geography as well, depending on how attractive those competitive choices are. And then there's a store layout, where the products are placed in store matters. If I have my highly visible promotions in a highly visible location in the store, then consumers will walk by those and are likely to buy those. So how the store is laid out affects how the consumers walk through the store, and the conversion of promotions or consumer traffic into purchases. So those are all things. There's a macro geography, where the stores are relative to your competition, relative to where the people live, and how easy it is the person to get from where they live to your store. And that similar concept exists on the internet. You have a website, your competitors have a website. How easy is it for the consumer to get to your website to find the products they need to buy? That there's a cost associated with the consumer getting to your website versus others, versus, how easy it is versus marketing they may get with embedded links. All of that is similar to the analogy of how expensive it is to get to your store in the physical world. So that applies in e-commerce as well. And then how your store is laid out, how efficient the store is laid out, how efficient your website, your web store is laid out, that impacts the transacting, and then all of these interactive effects. So that's the dynamics of retail, and we can assemble that into a set of differential equations that capture that. And so this would be the differential equations we see here. If you're technical, this is Poisson's equation, where we look at, grad squared phi is equal to a potential. It's a potential theory that can model the spatial interactive effects. If you treat every store in a market as a sink that's attracting traffic, and the consumers are the sources who have the money to spend, then the stores attract the people and the money. And so this is potential theory. If you've done any fluid mechanics, is one type of potential theory. So you could model geography with potential theory. So that's kind of one set of differential equations. And your potential theory has features like how attractive is the store, how difficult or what's the cost for a consumer to get from where they live to your store, how attractive are your promotions, where are your store locations, where are your competitive locations. So that's kind of the macro differential equations. The micro differential equation would be the path integral through your store. So you think of a path integral of your customers walking through your store. What's the optimal path through your store? Where are the products in the store? How are they laid out? What's your planogram look like? Where are all your products in the store? So you can say we can integrate the path that a consumer takes versus the products they buy, and try to minimize that path integral, which converts then traffic into transactions. So we can model transaction count as a conversion of a path integral through your store and your product layouts, convert traffic into transactions. So the macro level attracts customers to your store, then your store layout converts that traffic, the store traffic, into transactions, and then the quality of your promotion is this interactive effect. Am I making better decisions today than I made yesterday? Better decisions in terms of a better combination of products, a better combination of prices, better forecasts, better assortment plan, better planogram, all of those decisions. If I make better decisions, I will have a better outcome with the halo dynamics I described. So this is where we capture the halo dynamics as a differential equation, that this set of actions, prices, forecasts, items on promotion, this set of actions when I run that through my differential equation that captures those halo effects, I can model and simulate the effect. So this set of coupled differential equations captures the dynamics of retail or any retail business, be it food, electronics, clothing, sporting goods. We've been able to validate that this exists. And this simulation now, we can feed these dynamics into that reinforcement learning setup and actually simulate the impact of, if I promote this combination of items at these prices and I have this much inventory in every store, what will happen? These differential equations, these dynamics will allow us to do that simulation to find the optimal decision set that I can make. And so that's kind of how we apply reinforcement learning. Because we can't do a Markov decision process, we've emulated what the physics world does, which is create differential equations like Navier-Stokes, Einstein's theory of relativity, et cetera, that I mentioned before. And we've invented and patented a set of interactive differential equations. These dynamics really govern all of human behavior. And in retail, outlier effect is the fact that 10% of your customers are, 60 to 80% of your profits. In banking, 10% of your customers are more than 100% of your profits. In insurance and medicine, outliers, if you're different than the norm, you are likely sick, or you're risky, or you're fraudulent, or you're perhaps someone trying to hack into a network. So outlier effect is one way to look at decision making. Are you an outlier, and how do I treat outliers? Another one is this halo or interactive effect. If I do this, what else would happen? And the dynamics of business is a combination of interactions, which are captured in this kind of setup for retail, plus the effect of outliers. Is this granular entity, is this decision different than the norm? Is this person different than the norm and is an outlier? And I think all of human decision making, or most of it as far as I understand, and our science that we've used to create our science, is a combination of outliers and interactions. And that's the dynamic effect that we use to simulate all of business to find what are the optimal set of decisions I can make to get the desired outcome. So back to that original control theory setup, where if I do this promote these products at these prices and have this much inventory in the store, that's my system input and my desired action. I run it through my differential equations to see what will happen. And then I measure what will happen. I simulate this 100 million times in a week. I simulate years of retail faster than a human being can to find out the optimal set of inputs or actions to take to get my desired output, which is profit maximization. And this can be done completely autonomously. The system dynamics are the same from customer to customer. The only thing we learn from the data are some of the parameters like the halo effect, what's in the halo of product, that we can learn from the transaction data. We can learn some of the features in our differential equations, the halo, price elasticity, seasonality, those things we can learn from the data using machine learning methods. And those features then we plug into our simulation. So your data configures your universe. So for each customer has their own universe or their own laws of business and that we can simulate, but the mathematics is fixed. And we found at Daisy that this mathematics and science is consistent from customer to customer to customer. The only thing that varies would be those halo patterns, elasticity, seasonality, the product set, the competitor set, the geographic layout of where your stores are versus your customers or versus your competitors, where your customers live. Those, how your stores are laid out, those are what's different about your business compared to the competitors. And so that's Daisy's brand of reinforcement learning in a nutshell. One of the things we saw an academic paper written by Google DeepMind in October 18th, 2017, right, where they talk about AlphaGo Zero and how AlphaGo Zero defeated its world champion predecessor AlphaGo by 100 to 0. And it was trained itself in 3 days, playing 4.9 million games using reinforcement learning from nothing. So it had this amazing ability, learned in 3 days to play that. And so the game of Go is a simpler ecosystem than the world of business, as I described in a number of scenarios. But DeepMind at that time in 2017 believed it was possible to extend this approach to more complex real world systems, which is very consistent with the DAISY thinking. And so we've applied this thinking, wholeheartedly agree with that, and we've applied this reinforcement learning to win at the game of business. A game of business is which is more complex than these examples that DeepMind has. And we know that DeepMind and deep reinforcement learning is something that they've continued to evolve and improve. And we've seen other papers written by MIT that says, the era of supervised learning alone is on the decline, and it's really the combination of reinforcement learning, deep reinforcement learning. And we believe when you get into very complex systems that have uncountable state action pairs, that it needs some type of other dynamics, which, like we've done this differential equation approach, that's the next level of autonomous AI that will continue to evolve and grow and find more and more applications. So thank you very much for tuning in. Please feel free to follow up if you have any questions, or if there's topics you're interested in, or you want to be a guest and have a conversation with me. Would love to record those. So thank you so much for tuning in.